So, excuse me, just, there we go. Preparing my notes. All right. So, let me make some room. Last week, if you remember, we've finished to derive a second form, well, a second solution for the wave equation, or for the equation of the string, if you will. It was the second one we derived was the D'Alembert solution. I gave the name Bernoulli solution to the first one. So essentially, we might say that Bernoulli gave a solution in terms of standing waves or normal modes, and D'Alembert gave a solution in terms of what we had already learned to call waves. Some people like to speak of progressive waves to make sure there is no ambiguity with this term, standing waves. Personally, I would not use the expression standing wave at all. I don't find it particularly instructive, and I would rather speak of modes and waves. Okay. So I may start to begin reminding ourselves of what we've done so far. I may start by rewriting those two solutions as we obtained them last week. We decided to restrict ourselves to a case that is algebraically a bit more compact. So we decided that the initial velocity of our string is 0. Okay, we start from a situation of equilibrium. Well, a situation where when there is no equilibrium, but there is no motion, and then so we pull the string and then we let it go. Pull it, no initial velocity, and then tack, you let it go from a situation where there is no initial velocity. So D'Alembert showed that mathematically what happens next can be described and predicted by the following equation. U0 of x plus vt, let's call it x plus ct, plus u0 of x minus ct. Okay, and excuse me, and this is true as long as the initial velocity of the string is 0. Let me stress again this point. And remember, never confuse velocity, the velocity at which particles, chunks of the strings oscillate, with this parameter c that describes a speed of propagation along the wave. Remember, a wave is not a displacement of matter, but is a propagation of a disturbance. So the matter oscillates with a velocity that initially is 0, but that will change, of course. And the wave propagates with another velocity that I called c. And if you remember our previous lectures, it's related very simply to the ratio of the tension and the density of the string. And then we have Bernoulli solution, which you also should be able to find in your notes. And it reads like this. It's a sum, and strictly speaking, it goes from 0 to infinity of some coefficient that I might call alpha k, of the sine of kpx over L times the cosine of kpct over L. Okay, so this sign here is what we call the eigenfunction, the normal mode. This function, this cosine here, describes how this mode oscillate according to this pattern, this spatial pattern here, with respect to time. So people like to write this as cosine of omega k over t, where omega k is the ratio of k pi c over L. Okay, and it has the meaning of a frequency with respect to time. How many times a given point of the string goes up and down a full cycle over a unit of time. Oh, and notice that this frequency is fully determined by C and L. That is to say, by the density of the string, the tension that you apply to the string, and the length L of the string. K is just an integer. Okay, this guy can exist. This function, this behavior can occur on the string, provided that k is any integer between 1, sorry, not 0, and infinity. And pi is pi, 3.1415, blah, blah, blah. So, strictly speaking, if you remember the definition of wave that we gave 1 week ago or more, that's a wave. Okay, see the argument has x plus ct. That's a wave with that travels in the opposite direction, because the sign of this constant c has been reversed, but it's still a wave. You know, space and time appear in the same way as before in the argument. But strictly speaking, this guy is not a wave. It doesn't fulfill our definition of wave. Okay, so we will have now to do some careful analysis of the math that's on the whiteboard right now to convince ourselves that we haven't done anything wrong and that eventually these two solutions turn out to be coherent with one another. Okay, D'Alembert and Bernoulli. Basically, they are both based on well, D'Alembert solution is based on fairly simple math. It was difficult to show that it was wrong. But Bernoulli solution was supported by observation, because all you have to do to verify that this makes sense is to play a guitar, to play a single string on a guitar. I've told you a little bit about acoustics the other day. If you play a guitar string, you hear a nice harmonic sound, you hear a musical note, which means that indeed the frequencies that you're hearing must obey this, must be described by this expression right here, okay? So Bernoulli also had to be right, at least in stating that not any possible function like that could be a solution of the wave equation of the string, but only some particular frequencies could occur on the string. But that actually turned out to be a big and long dispute that lasted, I think, something like a century or so, until basically Fourier came about, and the work of Fourier came about. And the point of Fourier is that what Fourier discovered, and some of you might have encountered the concept of Fourier transform before, but if you haven't, it's okay, because we were going to see it now from a different angle. Fourier showed that for any function f, okay, any function can always be described by an infinite sum of sines and cosines. Fourier says that for any function f of z, there exists a set of values of, I'm going to call that AK, BK, nu k, or I'm going to use another index I. I'm going to use I. Okay, just to have no ambiguity with what I've done so far. Okay, if you prefer to use K, it's okay too. So there exists an infinite set of numbers. An infinite set of integer numbers 1 to 3 to infinity, such that f can be written as a sum of sines and cosines like this. So Fourier, so Bernoulli and D'Alembert are 18th century people. Fourier is a 19th century scientist, so it's a couple of generations later, I think, and I think a mathematical proof of this idea was only given by some of his former students, even later than Fourier's actually contribution. Fourier somehow developed this idea as a sort of hypothesis, and he used that to solve the heat transfer equation, if I'm not mistaken, the heat diffusion equation. But it turns out to be useful, this idea, it turns out to be useful for a lot of practical things. You can always write a function, any function, as a sum of sinusoidal functions. It's kind of crazy to think about it, but it is true, provided that sum goes to infinity, or in practice, that you let it go as long as it's needed to represent that function accurately, okay? It's a very important ingredient of signal analysis, because it's very useful, and if you do seismology, you will certainly realize it by practical application. It's very useful to decompose a signal in terms of its different frequency contributions at different frequencies. Okay, in acoustics, it's pretty obvious. When you play music, sometimes you like people like to control the contributions of the various instruments. So if you eliminate, if you decompose in different frequencies and then eliminate or turn down, reduce the coefficients that are associated to the higher frequency, you're going to hear the bass better. But if there's too much bass, you keep the coefficients of the higher frequencies unchanged, and you lower the bass. In seismology, it's kind of like the same thing. If you just want to study the surface wave, which, as we might be able to see within this very course, has very long wavelength, low frequency, you just filter away the high frequency, and then all of you see in your seismogram is this big late surface wave arrival. So anyway, that was an anticipation of things to come. You can forget about this for a second, and let's go back to the string. Okay, no filtering yet, no signal processing. All I'm saying is that mathematically, we know from the time of Fourier that any function f can always be written as a linear combination of monochromatic, as we say, sinusoidal signals. Monochromatic, this is a monochromatic signal in the sense that it has only one color, only one frequency. Okay, each of these terms here is by itself monochromatic. Okay, so then the next step to understand what's going on is to plug this expression here into our equation number one, and in particular into, well, to use this is what we call a Fourier series expansion. Is to do a Fourier series expansion of... Ah, grazie. Ah, bellissimo, grazie. Scusa, non rispondevo perché sto facendo lezioni. Ciao. Sorry guys, but it's good news because it means that finally I don't have to use a whiteboard anymore. But I have to learn to use this thing first. All right. So I hope I can use it before the end of this course with you. Anyway. Yeah, I'm very excited about this good news, but now let's go back to our lecture. So I want to do a Fourier expansion of this guy. Okay, so I'm to do that in a relatively painless way. I'm going to use some trigonometric equality once again that that I'm going to write on the whiteboard so that I don't get them wrong. So the cosine of a plus b is cosacos b minus sine of a sine of b. The cosine of a minus b is the same thing with a plus. The sine of a plus b is sine of a cos of b plus sine of b cos of a, and the sine of a minus b is the same thing with a minus. Okay. Good. So now I'm going to make a bit of room here. Ah, no, I deleted the one that I should have kept, but it doesn't matter. So we are going yes, no, well, doesn't matter. I need some room anyway, so I rewrite everything later, but let's, yeah, whatever. We'll get to that later again. So the next step is to look in the is to think in the D'Alembert. We're going to work on the D'Alembert equation. So in the D'Alembert formula, if you remember, I just deleted it, but I had this u0 of x plus vt, and then u0 of x minus vt. Okay, so first of all, I'm going to just apply Fourier expansion. And I'm just going to write the formula, which gives me u0 of, let's start, well, yeah, I mean, it will work. Let's do it for the minus first. So u0 of x yeah. Okay. Sorry. Yes. That there's one intermediate step that I shouldn't forget. No, that's okay. Just that it's here. I have a C, not a V. I'm sorry. Shouldn't have deleted the Blackbird. And I hope you don't mind, since we don't know yet this function. So it doesn't matter if I write, the only thing that we know about it is that its argument, x and ct have to appear in this form with either a plus or a minus here. So if I multiply this by 1 over c, that requirement is still fulfilled. So because that's going to make the algebra a bit easier later, I can essentially, when I do the Fourier expansion, I can use as argument x over x over c, and then I do the same for both plus and minus t. Okay, so let's think of that unknown function in this way. And let's Fourier expand it. Okay, u0 of x over c minus t is the sum over k of ak cosine of some nu k, and then the argument, which is now used to be z, but now it's x over c minus t. And then, I have again the sum bk sine nu k x over c minus t. Molto bene. And that's when the trigonometry becomes useful. Because look, here I have the cosine of a difference, here I have the sine of a difference. So if I apply, I have to apply the second and fourth formula here. So let's do that. The cosine of nu k x blah 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 is, or if you will, even better, nu k x over c minus nu k t. Okay, that's A. That's B. Formula number 2 here. It gives me cosine of nu k x over c times cosine of nu k t plus sine. So the signs of the same things. And now, I mean, you see what the next steps in this exercise are. For this, I do the sine. Let's do some of it. Okay, I do the sine of the same thing, and I get nu k x over c minus nu k t, and that's sine cosine minus sine, well, minus cosine sine. And what you have here actually already, it's quite an interesting result, because now we just use trigonometry and we are limited to sinusoids. Okay, I haven't generalized it yet, but just from this trigonometric equality, you see that a sinusoidal, this is what we call a sinusoidal wave. Okay, it's a wave because in the argument x and t appear in this way, and it's sinusoidal because it's the function is a sinusoid. Okay, so it's a cosine that propagates in space. So it's equal to actually the sum of two standing waves. Okay, that's one of Bernoulli's standing waves. It's something that goes like this without propagating around. It just goes, or like this, depending on how big k is, but it's just sort of stays in place, right? And that's the same thing, but basically, if you remember that the sine is the cosine of the same thing plus pi or something like that. A cosine is just a dephased sine. Basically, that's the same standing wave, but somehow shifted along the x-axis. And their sum, okay, if you sum two sinusoidal standing waves, you get a sinusoidal traveling waves. Yeah. interesting. So, but let's get to the more general result, okay? Because if I now substitute all that in my expression for u0 of x over c minus t, you know, this requires a little bit of algebra, but I don't think it's terribly hard. So I'm just doing it quickly for you. So you get alpha ak cosine. Yeah, I have to substitute all that into here. So that gives me cosine of nu k x over c times cosine of nu k t plus sine nu k x over c sine of nu k t and then I have to do the same thing for the sine. Make some room. There we go. BK. Oh, yeah, sine of nu k x over c times cosine of nu k t minus cosine of yeah, and the sine of nu k. Yeah, looks like I got it right, sorry. So give me a second. Now, I can now do exactly the same thing for the other half of the D'Alembert solution, which is the same thing with a plus, right? So the Fourier formula stays the same. I just have to replace the minus here with a plus. And the formula, if I do all my trigonometry and so on and so forth, it's very similar to what we have here. It's just, forgive me if I don't write everything properly, but basically, I mean, sorry, it's exactly the same thing because it's the same function, only the argument changes, so some signs will change in here. Basically, instead of a minus here, I get a plus, so I have cos, I mean, here I get a minus and plus dk, and here I get, yeah, cos sine minus sine cos. And then you have to sum these two things up to get the full D'Alembert solution and divide by 1/2. And basically, what happens is that if you do it properly, you should be left with the sum 1/2, okay, 1/2. So I'm just going to write the formula. 1/2 sum of AK cosine of nu k x over c times cosine of nu k t plus bk sine cosine. Yeah, cosine cosine plus sine cosine.
Sure.
Yes.
Sorry, sir. You can see on charts.
Say again. Oh.
Okay. Plus. BK.
Yeah, cos minus sine plus
But
bk cos sine plus.
Plus.
Thank you.
Okay.
Yes, you're perfectly right. It is correct in my notes, but thank you very much. Thank you very much. So, let's now look at Bernoulli solution again. Bernoulli solution was it was sum over k of alpha k sine cosine. sign of the spatial thing times the cosine of the time thing. Okay, so now if I take AK here equals 0, BK equals alpha K, and nu K equal to K P C over L, you can quickly verify that Bernoulli and D'Alembert solutions are exactly the same. Okay, you replace it, you verify that Bernoulli and D'Alembert finally are saying the same thing. So this is a good time to stop me if something wasn't clear. It's a very nice, very to me at least insightful results. It means that when you describe the behavior of a system that has some boundary conditions, so that has some normal modes and Eigen frequencies, you always have two possible approaches. One is to use the traveling wave approach, which in some cases can be very simple. I mean, remember, from the D'Alembert description, you see right away, you know, if you have a long string and you perturb it right here, what you're going to observe are two smaller perturbations of the same shape that propagate away from the center. Or you can use a normal mode description, which if you're a musician or a musical acoustician and you're worried about what kind of sound the people will hear, well, then you don't care so much about how waves propagate on your string. What you want to know are which frequencies will be excited based on the properties of the string, based on the initial conditions, and so on and so forth. But the two descriptions are exactly the same. I mean, are exactly equivalent. They are not incoherent with one another. It's important also that you, I think, that you keep in mind that the connection is made by Fourier theory, okay, by the idea that there's something magic actually in the cosines and sines, in the sense that whatever function, no matter how complicated it is, defined within an interval, you can always write it as a sum of a linear combination of cosines and sines, okay? Which means also that if you think of your string, any initial shape, no matter how complicated that the string might have, is always a linear combination of these guys. This will be important if you do seismology later on as well, because in seismology also we have two different ways of looking at the Earth. The normal mode way and the traveling wave way. Historically, people didn't really think about the free oscillations, about the normal mode of the Earth that much, because when you have an earthquake, you know, you're sort of like you're on a very big string and you're just very close to the point where the string starts moving, where the string is first perturbed and the perturbation, the disturbance starts to propagate. The people who started observing earthquakes, they were observing them in this way. In the old days, you didn't have the accurate instruments that we have today. So if you are in Europe, originally like 100, 150 years ago, 150 to 100, you were not able to observe an earthquake in Japan. There would be no sign of it whatsoever. So an earthquake was more of a local sort of thing, and people didn't even think that the earth would ring sort of like a bell. But with the advent of global seismology, okay, where we have network of instruments that are distributed all over the surface of the globe, including the bottom of the oceans even, it becomes possible to record even the effect of very far away sources. And if you put all this data together, and if you let the transient phase, if you wait until the end of this transient phase where many different frequencies are excited, then usually what happens is that the lower frequencies, the longer wavelengths are slower to dissipate, and a few days or even a few weeks after a big event, if you take a long seismograms and you take the frequency spectrum of it, if you decompose it in different frequencies and see how different frequencies are excited, you will actually see some very prominent peaks that corresponds to some specific modes of the Earth. Okay, so I've done the example of the string because it's a classic and because the math, as you've seen, are not so hard. If I had it's possible to do exactly the same procedure in 3D for a spherical body like the Earth. It's just that then the math would be much more cumbersome and time consuming. But the concept is sort of the same. You know, you have a finite body with some boundary conditions. In the case of the guitar string, you fix the endpoints. In the case of the Earth, you have an outer surface that is free of tangential stresses, is free to move. We call it a free surface. That's a limiting, that's a boundary condition too. You do all the math, you solve the equation in a way that's conceptually not so different from what we've done here. And again, what you see is that only a finite spectrum, not finite, but a discrete spectrum of frequencies is allowed, can be observed, okay? And these are called, to each frequency corresponds a certain pattern, like these cosines here of spatial oscillation, and these are called normal modes, together with their associated Eigen frequency. So notice that each spatial mode, each spatial pattern of oscillation has a corresponding frequency in time, okay? So, and the larger the wavelength of the mode, the lower the frequency. The larger the period, the larger the wavelength, also in space of the mode. Okay, so and people who actually write codes, algorithms to compute theoretical seismograms, they actually do use both approaches. So if a couple of years from today, you are asked to compute a synthetic seismogram, as they say, a synthetic seismogram, so a prediction of how a certain place at the surface of the Earth would oscillate because of an earthquake, you will look for a code on the internet and you will find, both approaches. There will be codes that actually use the theory of traveling wave propagation. They compute the ray paths from A to B, and they see what happens to a wave that travels from A to B. And there will be other people who calculate the normal modes of your Earth model, and then the code sums them up as much as possible without burning your CPU to get, again, in principle, the exact same seismogram. Okay, so questions, comments, anything that isn't quite clear? Sounds good? Okay. So I think as far as the stringer is concerned, I think we are good, and we can start to try to move to more to media that have more than one dimension, basically. And the first thing I would like to do, I still have some time today, is to think of propagation of acoustic waves in a gas. Please note the two words that I've been using, gas and acoustic. The terms acoustic wave is often in the literature, or in general in language, is used somewhat inappropriately and can be confusing. Many people will call acoustic even what we as geophysicists prefer to call seismic wave. Essentially, whatever the words people use, the distinction you have to make is between media that where shear stress exists and media that cannot be sheared. Okay, so you might have met the concept of stress before. There are many ways, and it can be very complicated to introduce it, but basically the way I think might be useful to think about it, stress are the forces that are all the forces that are applied on a surface of a given medium. Okay, so imagine that you take a chunk of material where waves are propagating, and there are some forces that are applied that tend to deform it, and so on and so forth. And imagine that you are able to take a surface, or no matter how oriented, etc., within that medium, and to measure all the forces that are acting on that surface. I'm not talking about weight itself, because weight, it's an attraction that concerns a mass. Okay, so it will act on a certain, you need a finite volume of material to have some, for it to be subject to some gravitational attraction. But if we just think of a surface that has no thickness, what we can measure on that surface are what we call surface forces. Now, in in what people sometimes call acoustic media, like gases or fluids, what happens is that the surface forces are always directed perpendicular to the surface that I'm talking about. Okay, you take any surface within the medium, no matter how oriented, and you measure the forces that act on it. A fluid or a gas can be defined as a medium where those forces are perpendicular to that surface. The moment it is possible to observe in these forces a component that's tangential to that surface, you're dealing with an elastic body. Well, no, elastic also is not the right word. You're dealing with a solid, I think is the right word. And yeah, in water, you can imagine that you can try to generate, you can try to shear it to generate forces that are tangential to some surface, but water doesn't offer any resistance to that, okay? It will just flow, like particles of water can flow tangentially with respect to one another, and they're not going to try to stop one another. What, I shouldn't say particles, but rather parcels of water, okay? A small, but not so small chunk of water. What fluids resist to is a change in their volume, okay? So pressure does exist. Yeah. So now, how do we attack the problem of describing wave propagation in a gas? Well, as usual, you've learned it with the string. The first step is to write force balance. So imagine now that this here, this little cube is infinitely small element of water, and we neglect weight in this first approximation, so it's a gas not subjected to any external forces, but some pressure might be applied to it, okay? So that means that to put in a different way the same thing that I said a minute ago, this pressure will be transmitted across this medium in the sense that if I put pressure on its outer surface, the matter near that outer surface will tend to move towards the inside of the medium, and the pressure, it will in its turn put pressure on the material that's neighboring it, that's attached, that's close to it in the opposite side as my hand. Okay, so if and this process propagates, quote unquote, across the whole medium. So if I take any surface anywhere across that medium and I measure what forces are acting there, I will always observe two things: that there's a pressure from one side, from the material of one side of the surface, that's applied to the material on the other side to push it, to compress it, and then equal and opposite to it, there's the pressure from the material that is being compressed to apply to the material on the other side. Okay, it's a resistance to this compression. Remember, Newton's third principle: to each action corresponds an equal and opposite reaction. That's one way of seeing it. So if you consider any parcel of matter within this fluid, it will be subject to pressures from all directions that might tend to compress it. Or if we reverse the whole exercise, that will tend to expand it. Just a matter of sign, really. So now, the way to think about it, in principle, if I tell you a parcel of matter, it could have any possible shape. So the main trick in continuum mechanics is that to think that if you work with a parcel of matter, that is arbitrarily small, infinitely small, if you will, you are allowed to basically think of it as a cube. The shape doesn't matter anymore because it's so small. We can always break something up in tiny little cubes, in tiny little bricks. So that instead of an arbitrary surface of complex shape, it's bounded by 6 equal faces of sides. Importantly, they have to be infinitely small, so I'm going to call them dx, dy, and dz. And then the total pressure, the total force that's acting on it, is the result of 6 pressures, each applied on one of the 6 faces. And because this is a fluid, the pressure is really just a pressure. There is no lateral stress. The pressure is indeed a force per unit area that's perpendicular to each face. Okay, so for each face I can draw a little arrow like that. So now what we need to do is we need to do a force balance for this element of mass. So, like, pressure in general is not constant, right? So in general, it will be also a function of the coordinates x, y, and z. Okay, so let's start from this point right here. The pressure applied on these sides here, if I call this point x0, y0, z0, the pressure applied to this side will be P x0, y0, z0 times dy times dz. That's the benefit, one of the benefits of splitting, of breaking up conceptually our medium into very small voxels, very small cells, very small cubes. That the only rule is that they can be as small as we want. They can't be big, but they can be as small as we want. So you can always make it small enough that the pressure can be considered constant all over this area here. that I darkened. Okay, so if within this area P is constant, approximately, then the force will be just P multiplied by the surface, which is dy over dz. Now, if I now think of the next point here, which is x0 plus dx y0 z0, well, pressure there will be, it might have changed a little bit. Okay, so the total force acting on this parcel of matter. Okay, so here I multiply by dy and dz, and from the pressure I get the force, okay? So the total force, and not pressure, acting on this cell here along the x-axis is the difference of these two guys. Why the difference? Because I'm not interested in summing the pressure that points in that direction. I'm interested in knowing what my parcel of matter is receiving from the mass that's outside it. Okay, so on this side, the material that's here to the left, it's either pushing it or pulling it, and here, but the positive direction would be this one, and here everything is in the opposite sense. What I'm interested in is the action of the matter here towards my mass. So I have to take the difference. And so that gives me P of x0 plus delta x y0 z0 minus P of x y z multiplied by dy dz. Okay, and that's basically the force. If I equate that to the x component, well, if I could equate that to the mass of my parcel of matter times its acceleration, and the force balance is done for the x-axis. For now, I'm just going to call this guy Fx, is the x component of the force. Good. So you realize that you can do exactly the same exercise for the z component and for the y component, the y component, okay? So if you do it, please, for now, believe me, but you can quickly verify on your own when you have some time, so that you would get for Fy, you would get P of x y0 plus the y z0 minus P, and this is multiplied by the x, the z, and for Fz, it's also very similar. I kind of keep confusing delta and d, but it doesn't matter for now, right? So now, what if I take this guy here and I divide it by the volume of my box? The volume of my box is dx, dy, dz. Okay? What I get, so here would be force per volume. What I get is, well, y and z cancel out, the y and the z cancel out. So I'm left with, well, this is just the definition of the partial derivative of p at x0, y0, z0 with respect to x, okay? Because remember, as small as we want, we can make this parcel as small as we want. So basically, it says we can be as close as we want to the limit where dx goes to 0. Okay? So basically, the point is that if I write as a vector the force, if I write the force as a vector, the first component is the oh, and there's a minus sign in front of all this, right? Why? Because p at x0 plus dx was pointing in the negative x direction. Okay, it's just a convention, but it's a convention I prefer to use in the reminder of this lecture. So allow me to do that. Remember, okay, that was my cube. That's the positive x axis, and p at x plus dx is pointing in the negative x direction. Okay, so we have to be careful with these things, otherwise, when we use that we use the formula in another context, we mess things up. So allow me to use this reference frame, and yeah. So what did we find? We find that the components of the force are proportional to the partial derivative with a minus of pressure with respect to the three Cartesian coordinates x, y, z. And that's all multiplied against c. This was force per unit volume, so we have actually, we shouldn't forget to multiply by the volume of our cell. So I haven't been using vectors much so far, but I hope it's okay if I tell you that when I underline here, it means that it's a vector, and with this notation here, I denote a three-component vector, and the first number here before the comma is a component with respect to the x-axis, y-axis, z-axis, and so on and so forth. And here we have a scalar that multiplies in the same way each component of the vector. Also, allow me now to take this occasion to introduce operator that's very useful in physics. It's a nabla operator, and it's defined as a vector whose components are the three derivatives with respect to the three Cartesian axes. So what do I mean by operator? It's a funny hybrid of a vector and a derivative, in the sense that it contains some derivatives at its components, but then you can use it the same way as you use a vector. So if you take if you multiply it by a scalar, you get another vector, which is, in our case, it's this it's this vector that has as its component the three derivatives of pressure with respect to the three Cartesian axes. We call this a gradient, okay? The gradient is when you apply the nabla to a scalar, and you still get a vector. If you, and this will turn out to be useful very soon, if you apply the gradient through another vector through a dot product, so the scalar product between the nabla and a vector u, that gives you actually the sum of the three derivative, actually of the derivative of each component by the corresponding Cartesian axis, and that is called the divergence of the vector u. That's called the divergence of the vector u. So this is just a review probably for many of you, but whatever, whether you've seen it before or not, it's something that will turn out to be useful, if not necessary, for the rest of this course. So let me use these final minutes to finish this force balance. So we have proved that the force, we can write it in different ways. So a more compact way to write it is that the force, well, for example, that the force per unit volume coincides with the gradient of the pressure in a fluid, in a gas. So now if I apply Newton's law to find an equation for the acceleration, just like we did for the string, notice that this conceptually, it's sort of the same thing as we did for the string, okay? We break it up in small pieces, and then we find the equation that each piece has to obey. So if I write the force as a mass times an acceleration, And you know, I might want to write this as a delta V to remind myself that this is valid as long as we're talking about a small parcel of matter. Now, the mass divided by the volume is something called the density. And so I can write this in terms of density. And this is what I got. So it's an important result. Notice that what, like right here, I wrote an equation that, like I said, it's valid for a small chunk of matter. But then here, the mass of the volume of this small box, of this small cell, cancel out. And what you're left is the density at a given point. And now, so you have an equation that has to hold point by point in the medium, and you can forget about your voxels, your bricks, your cells altogether. Okay? Every point, just like every point of the string, at every point of the string, the displacement had to obey the wave equation. At every point in the gas, the acceleration has to be proportional to the gradient of the pressure through density. Okay, and I pointed out here through my notation that each of these three quantities is an arbitrary, in principle, function of position. And also, I didn't write it, but of course, also of time. Okay, I can take your questions. We have a couple of minutes still. If you are confident with this explanation, I guess I can leave you until Wednesday. On Wednesday, so what we're going to do next, basically, is we'll, just like we did for the string, we are sort of doing the same kind of thing for the gas. What we have now, we have pressure on one side and acceleration on the other side. Obviously, the two things, besides besides Newton's laws, but they are not independent from one another. So we can add some further knowledge of how acceleration influences the pressure to transform this in a differential equation with only one unknown function. Eventually, what we want is we want to estimate how, given a certain initial configuration, the system is going to oscillate, it's going to be disturbed over time. So that's what we will see in the next lecture. If there are no questions or anything you would like to share, I'll stop here and say goodbye until Wednesday. Yeah? Thank you very much.
Thank you, sir.
Thank you.
I'll upload this immediately. Bye-bye.
Bye. Ciao.
Bye. Ah.